This screencast is going to focus on something called buffering capacity. So basically it's a buffer's ability to neutralize whatever stress is added to it. So we know that a buffer works because present in the beaker is basically an acid and a base. And so if you stress that buffer with an acid, it's the conjugate base that's going to neutralize it. If you stress that buffer with a base, it's the weak acid that's going to interact and neutralize it. So because there's something present that can deal with both, you get very little changes in pH, even when a strong acid or a strong base is added, because of this buffering capacity. So one thing we want to look at when we talk about a buffer is basically the magnitude of the amount of acid present and the amount of base present. And so this asks you to think about, from math, we've got the Henderson-Hasselbalch equation that pH is equal to pKa plus the log of base over acid. And so the whole idea of a buffer is that we want this pH to stay stable, right? And so if we want this to be stable, then we really want this to be a small number, or even 0 would be great. And so it asks you to think about, well, what could you take the log of in order to make this whole thing be 0? And the answer is, if you remember back to pre-cal or algebra 2, the log of 1 is equal to 0. So when our base concentration is equal to our acid concentration, then this equation simplifies to the pH is just equal to the pKa. And so let's say we wanted to pick a buffer that had a pH of about 4. Well, there's nothing magical about pKa, it's just the negative log of the Ka. So when you're looking at a table of acids, let's say you have one that's 1 times 10 to the negative 5th, and 2 times 10 to the negative 4th, and 3 times 10 to the negative 6th. Let's say those are all of our acid choices. And they say, I want you to make a buffer that has a pH of about 4. Then when you're looking at this, you want to pick the acid whose exponent is close to that pH. And then they may go on to ask you, well, what would the concentration of the base be, or the acid? And we'll deal with that in just a minute. But know that when these guys are equal, then the pH will just be equal to the pKa, and it'll be able to resist changes in pH. And so that's what this is talking about. And then they tell you to remember that when those guys are equal, it's the best buffer. The other thing I wanted to add, the bigger these concentrations, the more buffering capacity it has, which hopefully makes sense. Like if you had a 0.01 molar of the acid and a 0.01 molar of the conjugate base, yeah, it's a buffer, but those concentrations are so small that as you add the stress, the H plus or the OH minus, you're going to nix that pretty quickly, and that's going to be used up. But if you had like a 1 molar solution of the acid and a 1 molar solution of the conjugate base, you're going to be able to add a lot of stress, and both of those are going to be able to deal with it. But basically, when one of these is gone, or all used up, you're said to have broken the buffer. Like break the buffer is literally what they say. And so then that buffer will no longer resist changes in pH, and you're done. Alright, so this one example is not going to take us too long, and then I pulled up some more practice for us to kind of go through and talk about, hopefully get conceptually in your head what these buffers are doing. Alright, so it says, consider the acids listed on page 659 and determine which is best for preparing a buffer with a pH of 7. Then explain how you would make a liter of this buffer. So if you flip to that table, and feel free to pause the screencast so you can do that, you've got a long list of acids there. And remember, the trick is pH is equal to pKa, so we want to find the Ka that has an exponent closest to 7. Because the closer you pick to the pH that you want, the less you're going to have to mess with or adjust that base to conjugate acid ratio. So I believe the one that you find is HOCl, hypochlorous acid, and they tell you the Ka of that is 3.5 times 10 to the negative 8th. So the Ka is around 8, which is fairly close to our 7. Alright, so if we go ahead and we want to find the pKa, remember that's just the negative log of the Ka, and that comes out to 7.46. So we're fairly close to our goal of a pH of 7, and what we're going to do is we're going to adjust this ratio so that we can get it to be exactly 7. And so the Henderson-Hasselbalch equation is probably the easiest way to go about it. And so basically what we're doing is we're solving for this ratio. So they told us they want the pH to be 7. We already found the pKa 7.46. And then we're just going to do log of x just to make it a little bit easier. So negative 0.46 equals log of x. And to solve for that log, we do 10 to the negative 0.46 is equal to x. And x comes out to 0.35. Okay, well what does that tell you? X was our acid, or our base to acid ratio, right? So we want that ratio to be equal to 0.35. So an easy way to do that is to say that we want our acid concentration to be equal to 1 molar. And if that's the case, then what do we want our base concentration to be? That would be 0.35 molar. And so you could use 1 molar of our HOCl. And then let's think about what our base is, right? So this is a weak acid. It breaks up into H plus and OCl minus. So let's think of a salt that could include that OCl minus. And so the easiest is to pick NaOCl, and we would want that to be 0.35 molar. So that's how you kind of work backwards from the Henderson-Hasselbalch, right? Selecting from the table, just want your pH to be closest to the pKa, and then using the formula to figure out what you want that ratio to be. Alright, so let's flip to some of the practice. So this starts out 18 and 19 similar questions saying, of the following, which has the greatest buffering capacity? Now they haven't made it tricky in the sense that they've given you the same weak acids and the same salts, which is great, because then you're not having to compare like apples to oranges. So if I look at these, right, it's good when the concentrations are equal, but we also want the concentrations to be high. So when I look at like these guys, these are low concentrations. They are pretty close to each other, but you're going to exceed that buffering capacity pretty quickly. So the one that stands out to me is B, and 0.821 for your acid and 0.713 for your base, and that would have the highest buffering capacity. So for that one, our answer would be B. For 19, this is a base with its conjugate acid. So again, equal concentrations are great, but we want big concentrations too. So when I look at these guys, these are equal, but they're really small. And so that buffering capacity will be exceeded pretty quickly. So A would be our best answer for that one. Alright, now, like I said, there were some revisions to the AP curriculum, which you guys know about, and they've removed a lot of the math. But in place of that, they're really hitting these concepts hard. So although you don't have to do these intense buffer problems where they say, you know, what will the pH be when 0.1 mole of H plus is added, they are going to want you to be able to write reactions and to explain what part of the buffer deals with the stress. So let's go through these together. 22 says when nitric acid is added to an ammonium ion ammonia buffer. Alright, so first of all, we've got NH3 and NH4 plus present, right? And the thing that we're stressing is we're adding this nitric acid, which we know is a strong acid. So this is our base, this is our conjugate acid. So the cool thing about a buffer is you've got both of those sitting in the beaker waiting to deal with the stress. But make sure you get the right one to deal with the stress. If you're adding an acid, which of these guys is going to deal with that acid stress? It's going to be the base. So then your reaction will be NH3 plus H plus, and it's just going to accept that proton, because that's what bases do, and form NH4 plus. So then our answer would be A for that one. Alright, 23. Which of the following reactions happens when potassium hydroxide, so KOH, is added to an ammonium ion ammonia buffer? Alright, so same buffer, so we can carry both of these down. The same buffer, but now your stress is a strong base. You've got both of these guys sitting in the beaker. Who's going to neutralize a strong base? It's going to be your NH4 plus. So then you say, alright, NH4 plus is going to deal with that base stress. Remember, this is a strong base, so we don't want to fool with that K plus. He's just a spectator. So the NH4 plus is going to deal with the OH minus. He's the conjugate acid, so he's going to give up that H to OH minus, make H2O and NH3. So correct answer for that one's going to be B. Ugh, look at those guys. Yuck. Cation with a cation. Crazy stuff going on over there. Okay. Alright, 24. The reaction that takes place when a strong acid, they don't really tell you which one, but just H plus is good enough, to an acetic acid and acetate. Alright, so we've got this. It's acetic acid. That's our acid. And then we've got our acetate, which is our base. So the thing that we're adding is a strong acid. So you've got an acid present, you've got a base present, definitely a buffer. Who's going to deal with a strong acid stress? Well, that's going to be the base. So CH3, COO minus, plus H plus, he's just going to absorb that proton and form the weak acid back, so acetic acid. So will the pH drop a little bit? Absolutely, because you are making a weak acid, but it's nothing compared to just having raw protons floating around. Alright, 25. I like this question because you've really got to apply it and think about what's going on with the equilibrium. So it says, what change will be caused by an addition of a small amount of HCl, it's a strong acid, to a solution containing fluoride ions and hydrogen fluoride? So we've got a buffer because that's our weak acid, and that's our conjugate base. Okay, so if you think about this equilibrium, HF just hanging out, doing its thing, setting up this equilibrium, right? By coming in and adding this H plus, you're stressing that system. So which part of the buffer is going to deal with that H plus stress? You've got a base or an acid. The acid can't do anything to neutralize more acid. So it's your F minus that's going to deal with the H plus. And what's it going to form? It's going to form HF. So because of that, HF we would expect to increase. F minus we would expect to decrease, because that F minus is being used up to neutralize that stress. So when we go and we look for our answer, the concentration of hydronium ions will increase significantly. No, if it did, then that would be a big change in pH, and that would mean this thing's not a buffer, and we know it's a buffer. For B, the concentration of fluoride ions will increase. No. As well, the concentration of hydronium. No. C, the concentration of hydrogen fluoride will decrease. Don't think so. And the concentration of fluoride ions will increase. No. But you see why I did this first? Because these things are so wordy that you could get pulled in to one of the wrong answers. So do this first and think about it. Alright, so then D, the concentration of fluoride ions will decrease. Check. And the concentration of hydrogen fluoride will increase. Check. I think that's our winner. The fluoride ions will precipitate out of solution as its acid salt. And that's just nonsense, because it's not going to precipitate. Alright, so hopefully those practice questions have helped you think about buffers. Try the homework problems, see how they go, and we'll see you for the next screencast.